Hello, everybody. For those of you who don't know me, my name is Rafael Alves Batista. I'm a former postdoc at the University of São Paulo, where I worked at Professora Elizabeth's group. My work is pretty much related to the topic of today's and for the next lecture, which is Monte Carlo methods in astrophysics. Right. So yeah, today the topics that I'm going to cover is essentially all kinds of things related to Monte Carlo, not only today, but today and the next lesson. So today I plan on covering like a general introduction. Then I'll go through random number generators, which is essential, the heart of all Monte Carlo processes, random number generation. After that, I plan on quickly, or maybe not so quickly, it depends, reviewing some statistics, because Monte Carlo methods are extremely, they rely a lot on statistics. So you really need to be up to date with your knowledge of statistics, like all possible concepts, not only in one dimension, in several dimensions, as well as Bayesian statistics, which are also going to review here. Yeah, I don't know why I've put it in the last topic here. It's just out of order, sorry about that. And then I'm going to really introduce the Monte Carlo method. So Monte Carlo method, not just as a simulation method, but as an umbrella for several techniques, which include integration and sampling, like we'll see here. And I'm also going to illustrate a couple of astrophysical applications of Monte Carlo methods. Then maybe today or possibly in the next lecture, I'm going to talk about random walks and also introduce the concept of Markov chains. And these two things, random walks and Markov chains, as you'll see in the future, they'll come together when we start talking about Markov chain Monte Carlo, which is a very useful method for different kinds of things. So you'll see Markov chain Monte Carlo in data fitting. For those of you who work in pure astronomy or astrophysics or statistics, or if you are like an expert observational oriented, I'm pretty sure you've seen a lot of these Markov chain Monte Carlos for curve fitting and etc. I'm going also to present the Metropolis Hastings algorithm, which is the most famous and traditional Monte Carlo algorithm that we have nowadays. And as I said, this revision on Bayesian statistics is out of place. It should come together with the revision of statistics in general. And then I'm going to, towards the end, I'm just going to make a quick detour, although I'm not really sure it's a detour. I'm going to present how from Monte Carlo we can start moving towards more advanced concepts that nowadays play a big role in big data. One of these concepts is machine learning, like deep learning and so on. I'm not going to go into detail. We don't have time for that, nor is this the scope of this course. But I think it's useful to get an idea of at least some basic usage of Monte Carlo methods in machine learning, okay? I should mention that many of the examples that I'm presenting in this course, they are listed here on this website. So there are several Jupyter notebooks written with Python code to make your own analysis. For example, sampling techniques, you can go here, you can take your notebook and choose your function and so on and plot the curve, see what happens. Therefore, I have to say that probably this lecture, it might be more hands-on or more practical than the ones you've had before, right? And before I start, maybe I should also say that especially today in the first class, I think we're going to spend quite a lot of time in this revision part and laying the foundations for the advanced methods that we will learn, like the Markov chain Monte Carlo, for example. So today we'll probably spend some solid half hour or so just reviewing statistical concepts that are very, very important for later, okay? So let's get started. What is Monte Carlo? So Monte Carlo is technically a casino in Monaco. And actually this casino is the casino that gives the name of the method. So the story goes more or less like this. Of course, this is a very simplified story. As you know, in history of science and history of whatever, usually we mention a few people, but these people, they are not all responsible for the developments. There are always some other contributions, but of course, I'm just going to illustrate the key players here in the history, in the origins of the Monte Carlo method. So this person here, Stanislav Ulam, in 1946, so right after the Second World War, he was staying at home because he was ill, and he was playing a lot of solitaire, right? At some point, he decided to figure out what's the probability of winning a game of solitaire. He said, okay, so what's the probability of winning? So he tried a lot of combinatorial analysis and so on. It didn't really go anywhere, as you might expect, because it's a really advanced, really complex problem to be treated analytically, like he tried at first. Then he thought, naturally, okay, I'll just play a lot of games of solitaire and see in which fraction of these games I am successful. But in order really to get some decent statistics, given all possible combinations of solitaire, which you can do that by hand, estimate all possible, the total number of games. He said, okay, I might just play a lot of hands and then just count the fraction of them in which I'll win. Yeah, but after some time he realized this is a useless endeavor because I'm going to spend years just playing solitaire and I'm not going to cover not even 1% of all possible games. So I don't have enough statistics to do that. So he had the idea, okay, I cannot do that, but maybe a computer can do that for me much faster. So he asked John von Neumann, perhaps one of the greatest mathematicians of the 20th century. I don't know if you've heard of him, probably yes. And he's very influential also in computer science and so on. So at this time, John von Neumann, he was working in projects related to one of the actual first large-scale computers for scientific applications. And Ulam asked John von Neumann whether it was possible to run this in a computer, right? The name of this computer was ENIAC. ENIAC. Yeah. And it was based in a US military place. And yeah. So anyways, and John von Neumann, and he started implementing this kind of Ulam's idea, you know, just to check everything in a computer, which is much faster. And the actual name Monte Carlo was suggested by this third figure here, Nick Metropolis. You see Metropolis, his name, coming back later on because his algorithm, it's the first proper, like it's the first real Monte Carlo algorithm for general purpose. It's still largely used with, of course, some adaptations and so on. So yeah, Nick Metropolis, he because they were friends, he said, okay, Ulam, your uncle always asks you money to gamble, so and he always goes to Monaco for that, so maybe we can name it Monte Carlo, this method, because you know it's a gambling money anyway, so it's a gambling problem that they were treating in the computer. That's the origins of the name Monte Carlo. Of course, I didn't tell this story quite well. You can hear this story quite well in this. You can read about it in this paper, which was written by Metropolis himself. It's a very interesting early history of the Monte Carlo method. And this picture here at the top, it shows a bunch of cables and stuff. This is the ENIAC computer. So ENIAC stands for electronic, yeah, I don't really remember that, sorry. But this is the computer that did the calculations for the hydrogen bomb at the time. So not for the Hiroshima bomb, because this is 1946, but for like other tests during the Cold War and so on. So this computer really had, really played an important role during history. Okay, so yeah, and interestingly, at this time, the program, so the first Monte Carlo codes that were run here by these people that I just mentioned, they were written in the old programming style. I don't know why I said codes, because it's really programming. I mean, although it's not the programming we are used to, like for, if we don't type that. They had these punch cards and you had to put like 1 million of these cards and then let the computer run. So it was much more complex, no memory and so on. But yeah, it was successful in doing Ulam's calculation and also in doing some bomb calculation for the hydrogen bomb. Okay, let's move on. Let's get moving on. So if you're interested, read that somewhere else, because I don't really know all the details, but it's an interesting story. So what's Monte Carlo? So Monte Carlo, it's more like a method, an umbrella for several classes of applications. And this class of method, it's based on the use of random numbers to generate a particular problem. These random numbers supposedly should mimic what we expect in reality. And we tell our Monte Carlo code or our Monte Carlo method what's reality based on some probability distribution functions that we give as input to these codes in general. So yeah, Monte Carlo method, it's just this umbrella of different things that we can do. Monte Carlo simulations, that's something else. So Monte Carlo simulations, that's just the application of Monte Carlo method. So like random numbers and some kind of sampling to obtain some kind of statistical behavior of a system or phenomenon that we are interested in. But we do need to have some knowledge of this phenomenon to just provide our Monte Carlo code with this information, right? It doesn't come up with ideas on its own. And this third point, I think it's the most important one for Monte Carlo. Monte Carlo uses random numbers. And this is the key for the whole thing that we're going to talk today. Monte Carlo uses random numbers. And among the applications, we can do simulations with Monte Carlo. We can use Monte Carlo to do integrals, like simple integrals, but also multi-dimensional integrals. We can just use Monte Carlo methods to investigate the landscape of probabilities and do some kind of optimization, looking for minima or maxima. We can use it for some Bayesian hierarchical modeling and machine learning, which I'll just briefly touch towards the end. Okay, let's define what random numbers are. And I like this cartoon a lot because that relates to probably our misconceptions of what random means. So in this cartoon, you can see the first one here. Over here, we have our random number generator, 9999. Of course, if the number keeps repeating, we'll probably ask, are you sure that's random? Because the number is repeating, right? So we probably wouldn't expect that to be random. But that's the problem. With randomness, you can never be sure because it's random. Things may come out, however unlikely it is. You may, for example, toss a coin and get like 10 heads in a row. It's unlikely, but it's possible. It's not impossible. And that's the whole point. Another interesting problem that happened a few years ago when Spotify, I think most of you have used it and probably use it nowadays. So a number of users were complaining that in the earlier versions of the software, they were clicking on like there is the symbol for the shuffling, right? It's just this, like two arrows crossing. It's the universal symbol for shuffling. And apparently their algorithm was not shuffle. It was a random algorithm. So the same song was played in a row sometimes, or sometimes song A was played, then B, and then back A again, right? Which is not what the users probably want, because the users probably wanted to have it shuffled, just a random order of all the songs, but without the repetition until the cycle with all the songs is completed. So this is just one point that I would like to mention. Random is different from shuffle. Okay, random can be just anything you don't know. It's just random, things may happen. So how do we get random numbers? Nowadays, the computer provides random numbers to us. It's relatively easy. There are some algorithms that takes the computer clock or the time or whatever, and then generate a random number based on that. But in the early times, in the 1950s, for example, right after those people that I mentioned, they started using the Monte Carlo method. How did we actually get random numbers to do Monte Carlo? So you could look it up. There were these huge books with millions of random numbers. Like one page of this book, it's like this. It's completely, these numbers were randomly generated and they just printed it in a book. Nowadays, we can just take it from the computer, but at that time, this was not available. So this is one way we can get the random numbers from a book. Not very convenient, but useful in the past. Nowadays, we can use, for example, some algorithms like this linear congruential generator. So the idea here is that we have a multiplier, A, which multiplies something called xk. And then we have this increment, which is just an increment, and then this modulus. And then this x0, for example, it's the seed. So it's the first one that is used to generate the whole chain of random numbers. So we have an algorithm to generate these random numbers. Therefore, because we, in this case, there is an algorithm behind it, random numbers are not truly random. We call it a pseudo-random number generator. It's not truly random. When performing Monte Carlo simulations, you're coming back to that soon. So you don't, at the moment, you don't need to know how to do Monte Carlo things. You just need to know that it relies on random numbers. And you need to know that random numbers, they usually are associated with a seed. So the x0, the first one that defines all the subsequential random numbers. This seed essentially allows for reproducibility. So for a given seed, the same numbers will be generated in the same order. And therefore, if you run your simulation and I run my simulation, and if they have different seeds, they will probably be statistically compatible with each other if the sample is large enough. But if we use different, the same seed, they're going to be exactly the same distribution. So it's important whenever you're doing a Monte Carlo simulation, if you want your results to be fully reproducible, you have to write down what seed you're using. And one interesting thing is that these random numbers in a typical computer, nowadays they are like 64 bits or 32 bits, mostly 64. But let's take 32 bits, for example. So the maximum integer number that can be stored in this computer, like in a 32-bit, it's 2 to this power minus 1, okay? So that's the maximum integer number in a 32-bit computer. Therefore, you can only generate random numbers up to this, the maximum integer corresponding to the number of bits in the computer. And that, therefore, gives a periodicity. If, for some reason, you came up with a code to generate random numbers, after you've reached a number of cycles corresponding to the maximum signed integer of your computer, the random numbers will just keep looping over themselves. So that's a kind of periodicity, and that's probably the limit of your random number generation. Okay, you should keep that in mind. For most practical purposes, at least for me in particular, I never had this problem because I don't think I ever had to generate 2 to the power 30 something random numbers. Never. Usually, you know, things are time consuming and I'm usually happy with a million or so. But okay, I don't know what your application is going to be after you learn this. So keep that in mind. This method that I mentioned, the linear congruential generator, It's just one among several other methods. There are better methods to generate pseudo-random numbers. Okay, this is not the best one, but I think this is more useful to build our intuition of how this chain of random numbers is generated. So the first ideas of how to generate random numbers, it goes back to, again, von Neumann in the same time, like right after the Second World War, 1946. So he developed this method called middle square method. So essentially the idea is the following. You'd get a number, let's suppose a number with 4 digits, like, just a number of 4 digits. If you square this number, then you get like an 8-digit string of numbers. And then you can get just the middle 4 ones, and that's a random number. Okay? So if you keep repeating this procedure, and then these other 4 that you get, and you can square it again, and then get the string of 8 digits, take the 4 central ones again, and keep repeating this. This is a way to generate random numbers. Okay, this is called the middle square method, as first devised by von Neumann. It's not very good, it's not the best one, but for the time that was exceptionally good. I mean, it did its job for the time. Okay, now it's time to move on to statistics. So we should review some basic statistical concepts. I'm pretty sure all of you here, because this is an advanced course, right? I'm pretty sure you know most of these things, but I think for those of you who are not that comfortable with it yet, I should mention it again. I'm sorry if I'm going too slow, and that's the good thing about recording the video, right? Maybe you can just skip forward if you don't want to see this revision. Maybe you can just watch everything, or watch in speed 2. I don't know, whatever you want. If you're comfortable, you don't need to see this, but I think it's important to really recall all these details, because most Monte Carlo methods, they are based on statistics, because essentially we have random numbers being generated, but these random numbers, they are usually used to draw a sample or something from a distribution. And a distribution here, it's a probability distribution function. So a random variable, capital X, it can assume all values in a given domain D, and we can define a probability distribution function for this random variable, capital X. So the probability distribution function, it essentially gives us the probability of each value, so small x, of x to occur within an infinitesimally small interval, x and x plus dx. We call p of x, or the probability of the random variable x to assume this value x, we call this the density function of the probability, or the probability density function, or that. So the probability of finding x within a given interval, it's just, by this definition here, it's just given by a simple integral. So it's the probability of finding x between a and b. It's just the integral between a and b of p of x dx. Another important concept, which is probably trivial for most of you, but anyways, another important concept is the concept of the cumulative probability distribution function, or CDF, which is capital P of x. The CDF gives the probability of a random variable x to assume any values that are smaller than x. Therefore, by this definition, we just integrate the probability distribution function from -infinity up to the value of x. Note here that the CDF, it always increases, right? Because as you increase x, so does p, capital P here, so the CDF. So this function is monotonously increasing. Keep this in mind, because this will be very useful for our sampling algorithms that will come back later when I present one of the methods, the Monte Carlo methods for sampling. Okay, the CDF and the PDF, they are obviously, based on that definition, they are related to a derivative or an integral, depends how you see it. And obviously the PDF should be normalized. So the probability distribution function P of x for all values of x in the domain, it should be 1, right? So you should just integrate it to 1, or if it's discrete, you should just ensure that the summation is 1. At this level here, I assume that most of you are comfortable if I just keep moving when I talk about statistics between the continuous case and the discrete case, because I suppose that because this is a graduate course, you should be more comfortable with that, okay? So sometimes I'll say integral, sometimes I'll say summation, but in the end of the day, they will probably be the same thing, unless otherwise stated. So we also define the statistical moments of a distribution as the average of a given value of x to the power of a given variable x to the power n. So this is essentially just the probability distribution function weighted by whatever is inside these brackets here. And this defines the central moments of a distribution. So x minus the bracket x to the power n. We can also write this integral. And there are a few concepts that just come directly from here. So if n is equals to 0, that's obviously the normalization, which is, yeah. But it's not an interesting case. The interesting case starts to be at n equals 1. So if it's n is equals to 1, then we have the first statistical moment, which is the mean. The second one, that's the variance. The third one, we have the skewness of the distribution. The fourth one, it's the kurtosis. I don't know about the fifth one. Probably there is a name, I don't know. I've never actually used it in my life. So yeah, but anyways, the procedure is outlined here. Okay. So suppose now that we have a function of a random variable. So let's say that f of x, a random variable x, that's y. Okay, now you just want to really outline the very basic things that we can say about this relation. So if we have one random variable that it's a function of the other one, then like we can start writing things. So the probability of a given random variable capital Y of Y, that's the probability of Y being less than Y, small y. I'm saying Y a lot, yeah. And it's not because I'm from the state of Minas. Okay, so if Y is a function of X, we can just write as follows. And then we can just invert this term. So X less than F minus 1 of Y. And we finally get that this is the CDF for X for this term, which is just the inverted one. Therefore, we can relate the PDF and the CDF, we can relate the PDF for Y and for X, remembering that Y is just a function of another, it's one random variable that's a function of another random variable. We can just relate these two things through the derivative, and if you keep doing this substitution, Y, it's the inverse of Y, then we make it X, and so on. Yeah. This is just a simple algebraic manipulation, okay? We note that in order to do all these things that we are doing, the function should be invertible. And if that's true, then we have that the CDF is always a monotonous function, which is obvious, as I said before. This idea here of inverting functions, one function is one random variable is a function of the other. This is the idea of what's going to be called later inversion sampling. We are going to see this in a little while. And there is something that is very important here for the discussion. Actually, not for the discussion, but for the calculations that we're going to do towards the end of the lecture, which is essentially just recalling Bayesian inference. Okay, so what's Bayesian inference and how is it useful for Monte Carlo? Well, in the end, we are going to see that when we apply Monte Carlo for modeling, for curve fitting, and these kind of things, Bayesian inference will be really important. So the whole idea of Bayesian statistics is just, it's based on these two rules here. Two rules and one theorem. Yeah. So we have this sum rule, which is just that the probability of a given value, of a given x, is equals to the summation. Again, just keep in mind that we might be in the continuous case, so that would be an integral. It's equals to the summation of p of x and y. Okay, so if you have two variables x and y, and you want just p of x, you just integrate over y. Okay, so that y is completely absorbed in x. The second one, it's the product rule. So the product rule, it's essentially p of x and y, that's p of x, and p of y given x. So that's how you read this. This is a conditional probability. So conditional probability tells us that given x, so the probability of y given x, so the probability of the first given the second. Okay, you've seen this before. I don't know how comfortable you are with this. You might have forgotten. And now we come to what's called Bayes theorem. Bayes theorem, it's named after this this person. He was a reverend, I think, of the Catholic Church, if I'm not mistaken. Maybe wrong here, just guessing. And Bayes theorem essentially states the following. Let A be an event, and let we take a number n of samples, so B1, B2, B3, up to n. Okay, so the probability of observing any given B, any B given this event A, is the probability of observing A given B, K, where K is just an index from 1 to n, times the probability of this one here, Bk, divided by the probability of A, of the event itself. You can just rewrite this in a more convenient term with this summation. Yeah, this is just a way of recasting things, because then you can just rewrite this P of A as the summation here. Yeah, you can easily show that, okay? But why is this interesting and why is this important? This equation, essentially, the whole, Bayes theorem really changed everything. It changed the world in some sense. Nowadays, this is the core, like for things like machine learning, for example, for fitting data, for comparing models. So which model should we accept, which model should we reject, and so on. Bayes theorem tells us that any new piece of information, as I've written here, it can teach us something new. And it also tells us that we can update our prior beliefs based on any new evidence that we have. So, for example, let's suppose that we started with just one sample. Then we have this. But as we draw more and more samples, this term will start to make an effect, right? We start just with one. Therefore, if we start with one, it doesn't really change anything, but then it's two, and things may change, and then three. Therefore, our picture of the world or of something, the way we describe some kind of probability, it changes based on every new piece of evidence that we are learning, okay? And there is also, I'm using the word beliefs here, and yeah, I'm not really sure that's technically correct, but I think it is. Probably, I'm pretty sure some philosopher of science already discussed this, but I think beliefs is probably the correct word. And why am I mentioning all this? Because, as you might know, there are two schools of thoughts in statistics. One is called frequentism. It's the one we usually learn. So we count how often something happens, the frequency of any given kind of any arbitrary event. And that tells us a probability. But in Bayesian statistics, that's something more subjective, because Bayesian statistics is really centered in Bayes' theorem. right? So that's why it's sometimes called a subjective interpretation of statistics. So this term that I'm highlighting here with the mouse, as you see, this one, it means that we are constantly updating our knowledge. Therefore, for the frequentists, usually there is a frequency of an event, period. You just measure the frequency of something happening. But for the Bayesian is always updating its knowledge of a probability based on each new evidence that comes in. It might sound like the same thing, but it's not, because Bayesianism, it refers to our degree of confidence in a model, whereas frequentism, it's more objective. You know, our mathematics is describing the model, it's describing the data, and for the Bayesian, there is an intermediate step, kind of. It's just a way of thinking, okay? But moving on. So this is just a way to recall Bayesian modeling. As you can see, this expression is just a version of a Bayes theorem under some guise. So it's just Bayes theorem disguised. Let me name things. So theta here, it's a parameter. For example, if you have like a given model which is linear, like a straight line, ax plus b, theta here, it's either a or b, just a parameter of your model. Your model is defined as m. D, capital D, it's your data. Let's define what these capital P's are in this sense. They are all probabilities, right? But they are different probabilities. So this one on the left-hand side, it's called the posterior probability of theta given the data and the model. Okay, this. Here we have the likelihood of theta in model M. Here we have what we call the prior probability of theta. And at the bottom, in the denominator, we have the model evidence. So the probability of D given the model. So the probability of, yeah. So for a given model and a given data, this is the model evidence. What's, yeah. The prior thing, you know, this is the probability of theta, a given parameter. But this, if you have to input this in your equation, in Bayes theorem, you are telling the equation your prejudices about something. So you have a preconception of what the distribution of a given theta should be. If you don't know anything, you just say, okay, they are all equal, right? This is what Laplace, you all know Laplace from many other things, astronomy, etc., who is actually the person who named Bayes theorem, Bayes theorem, by the way, gave the theorem developed by Bayes the name Bayes theorem. It was Laplace. Yeah, but this is what Laplace would call the principle of insufficient reason. If there are no reasons to think otherwise, agents like you or me, we should ascribe equal credence. So we should believe everything, all possible outcomes equally. So we should ascribe equal credence to all possible outcomes. In Bayesian statistics, that's a uniform prior. So I don't know anything, so I'll just say that they all have the same weight, right? But the world doesn't behave like that. Some priors, you know, there are some things, you know, we cannot say that it's all uniform. So takeaway message from this particular equation is there is a lot of complicated philosophical discussions concerning priors. And yeah, so priors essentially reflect our subjective views of things. Okay, when multiple models are used to explain a given data, like through this equation, for example, we have the model M and the data D. We are faced with the question of which of this model is better. Where better, I mean, we also have to define what better means. There is no unique definition of better, and it depends depending upon what we mean by better, we can come up with different criteria to compare different models, right? Usually, we can have like two different schools of thought. One is we compare the probability of the model given the data, and we compare the expected predictive accuracy of the model by every new piece of data that keeps coming, right? So you just keep updating your model. Okay, the first one that I mentioned, which is essentially just to compare the probability of the model given the data, it's essentially just the Bayesian approach, right? It's called Bayesian model comparison. And the latter one, it's more related to the frequentist approach. It's a slightly different interpretation. And when we want to make predictions, for example, we want to make predictions related to something that we call here y. So if we want to make predictions, we just integrate this y given theta, d, and n. So we just integrate over all theta, so over all possible parameters. That's how we make predictions. However, keep in mind that by doing this, by making this prediction within a given model, of course, you see that m is present in all the terms. So it's for a given model and a given data set. But when you do this, you should notice that within this Bayesian framework, there is the issue of the prior again. So our subjective impression of what the prior should be, this one, it might affect the outcome. And how do we compare different models using Bayesian reasoning? So it's just according to this equation. So the probability of the model given the data, it's equal to the probability of the data given the model times the probability of the model divided by the probability of the data. And the probability of the data given the model, it's just the integral of this. So as shown here, the probability of data as a theta and model times the probability of theta and model. Okay, so this is how we compare two different models. So we see which one better matches the data. And what I find very cool about all this is that there are actually ways within the Bayesian framework to discriminate between two models, right? If we have a given data set, which of these two models is better? Well, usually in philosophy, in science, we always learn that we have this Occam's razor, right? Whichever explanation is the simplest is the one we should choose. So Bayesian modeling actually also has some internal structure to, if two models are essentially the same result, Bayesian reasoning also favors the simplest one, which is very cool. I'm not going to go into details. I think I've extended too much, but there is this very cool cartoon that I always like to show in the context of this Bayesian discussion, which will come back towards the end. So this is not useless, okay? It might seem like I'm diverging, but I'm not. Bayesian will come back in the end, especially when we talk about Monte Carlo fits. There is this cartoon that I always like to show regarding Bayesian inference. So did the sun just explode? So someone asked, so the neutrino detector measures whether the sun has gone nova. Then people run two dice, and if it comes out two sixes, then it means that the sun exploded, right? And then for this simple problem, there are two interpretations. Like a frequentist approach is, okay, if we roll the dice two dice and we get two sixes, then which is the chance is like 1/36, 0.027, then it means that the sun has exploded. But the Bayesian statistician will probably say, yeah, I bet you 50 that it hasn't. This is an XKCD comic. There is a lot of philosophical discussion embedded in here, which I'll not get into, but I find it very interesting. However, why I find this funny? Because actually, yeah, Bayesian is a subjective view of statistics. So it's funny because the probability that someone will have to pay the $50 if the sun explodes is essentially zero, because the probability of surviving given that the sun exploded is virtually zero. So the Bayesian, taking this into account, will probably bet whatever you want, because you know you'll never have to pay this bet. That's why it's funny, in my opinion. But yeah. Okay, continue with this this brief statistical, or no longer that brief statistical review. We have that for univariate, so just functions of one variable, we have these expressions that we know for the variance and the mean, and we have the statistical moments, but we are also interested in the multivariate case. And the multivariate case is where we have x, y, z, or x1, x2, x3, and so on. So we have like multiple random variables. In this case, the statistical moment is this. Essentially just a generalization of the previous definition. But if we have a given number of random variables, there is a fundamental thing that probably some of you who are doing working with data analysis, probably you might have stumbled upon this, which is the covariance. You might have heard the term covariance matrix or something like that. So the covariance between independent variables, it's essentially zero. But the covariance between any two random variables, it's calculated as the mean of like a given xi minus the average of all xi's. Same thing for j, the product. And this is equivalent to this integral. That's the covariance. Independent random variables will give you zero. This is kind of the orthogonality condition in linear algebra, like you know, you have that two vectors, they are orthogonal. And this is kind of the same. So the covariance matrix it just gives you a kind of non-orthogonality between things. So it gives you a mixing. Okay. Moving on, I promise this is my last slide on statistics. I know for some of you it might be boring, but I think it's important to discuss. Especially this one, now it's the central limit theorem. So the central limit theorem, it will come back later for the Monte Carlo. It's actually the basis, the statistical justification for the Monte Carlo methods, okay? For many Monte Carlo techniques. And this theorem tells us the following: for sufficiently large samples of a given population, the mean values of random samples are normally distributed. And let me say this again: the mean values of random samples are normally distributed, not the samples themselves. So if you have a bunch of events, you don't know how it is distributed. But if you take the mean of each one of these, and then if you make a histogram, you see that it will be a Gaussian, okay? That's what the central limit theorem tells us. And the variance of any sample is just approximately the variance of the whole population divided by the size of the sample. So yeah, it's just a kind of scaling relation, right? Because if you have a smaller sample, yeah, the variance will be probably smaller, okay? So let x1, x2, up to xn be a set of independent variables with arbitrary distributions. Then we have that y, I'm just calling y, is the average of xi. Okay, so essentially this is virtually kind of the mean. If you plot the distribution of the means, these will be normally distributed, okay? You can probably prove this, or if you haven't done already, in the statistics course that you had a couple of years ago, I suppose. This is a statement that can be easily, it's never easy, but yeah. Nowadays it should be easy if you really learned it. So it can be easily proven. Okay. Now it's time to move on to Monte Carlo simulations. So what is a Monte Carlo simulation? A Monte Carlo simulation it's just a procedure in which we want to estimate some unknown values, and we want to infer what these values are, and we generate random numbers according to a given law in order to get this, okay? So we draw random realizations of whatever, of a given scenario. So we just define which scenario we are interested in. These random realizations is like the same as observing something many times. So observing a phenomenon many times. And then this method, the Monte Carlo method, in the context of simulations, it enables the estimation of like many things out of this sample, out of this population that you simulated. But one of the very interesting applications is just, to take into account also statistical and systematic uncertainties in cases in which we don't have analytical solutions. Towards the end, in the second lecture, one of the last things that we're going to see, we're going to do a full example of Markov chain Monte Carlo fit of a model. And then we are going to see what I mean by saying that both statistical and systematic uncertainties are taken into account. We will essentially just compare a simple fit using the procedures that we are used to, like least squares, and then we are going to do it using Markov chains. And then we are going to get different results, which is nice, which is cool. Okay, so the classic example of Monte Carlo simulation is the estimation of pi. You'll see this in every single Monte Carlo lecture in Wikipedia. In fact, this figure here, I took it from Wikipedia, okay? This is the classic Monte Carlo example that we see everywhere. But in fact, this example, the idea of estimating pi from Monte Carlo simulations, or not from Monte Carlo simulations because there was no Monte Carlo, but the idea of taking a lot of something, like a large sample of something, and then trying to estimate the value of pi, it dates back to the late, I think, 1800s, maybe 1780 or whatever. There is this problem that it's known in mathematics as Buffon's needle. So the idea is the following: you get a lot of toothpicks or needles or whatever, and you just let them fall. You want, and now you assume also that your floor or the table or whatever the needles are falling onto, it has a bunch of longitudinal stripes. Then the question is, what's the probability of these parallel stripes of wood, each of course with the same width, and we drop the needles. Then what's the probability that the needle will lie across a line between two stripes? That's the problem, okay? And this problem also allows you to calculate, to estimate pi. But here we are going to do it differently. So let's start. We know that the area of the circle is pi r squared. If we just take one quadrant of the circle, so if we just cut the circle in 4, it's pi r squared divided by 4. We know that the equation of a circle is x squared plus y squared is equals to the radius squared. For simplicity, let's just assume that the radius is like 1. It's the easiest case. Therefore, we can say that y is equals to the square root of 1 minus x squared. And if we perform this integral, that will be like pi over 4. Now we can consider n random points, just n is the random number of points, the number of points, okay? And we can do the following. We can just keep throwing a lot of points within a given area and counting how many of these fall within a given, fall within my circle. And this fraction, as you see here in the end, like the 4 times the number of hits, so the number of numbers that you do randomly that falls within the circle divided by the total number that you've thrown, this gives you the value of pi. Of course, this problem, in the way it's constructed, you have a circle inscribed, so it means that it's touching here it's inscribed within a square. And we throw a lot of things, like in X and Y directions, we throw a lot of random numbers, and we see how many of them fall within this circle and how many fall outside the circle. That's a simple, as you'll see later, acceptance rejection Monte Carlo. Okay, let's see what happens. So as you keep throwing more and more of these points, you see that the value of pi, it keeps going closer to the actual value. Yeah, you can probably, sorry. Yeah. So as I told you, I have the GitHub page with many examples. So I think I'm going to cover the lecture and then I'm going to open the page and get onto the examples. Or maybe should I do the example now? No, I'll come to the examples later because let's just continue, okay? If you do this example that I just did, we'll get these plots. So this is the distribution of the values of pi. You see that you get like pi is equal to 3.0 something or 3.3, but most of them, they are really close to 3.14, 15, 9, 2, 6, or I don't know how many digits of pi you know. Yeah, there are people who know like 100, I don't. Anyways, yeah, so you see that most of the peak of this distribution, it's really close to pi. So most of it, it's really close to the actual value of pi. But how many random values of pi were required in order to really start getting close to the value of pi? So the real value of pi is denoted by this dashed line here. You'll see that if we just take 100 values, it's not good enough, not good enough. But as we get close to 10,000, we start approaching the value of pi. That's when things start to converge. You see that the value of pi, it's like, you know, it's really close to the actual value of pi. It's maybe 3.15 or 3.13, but it's not 3, okay? And the whole idea here of convergence is we have a large enough sample, and a large enough sample really gives us something like, it allows us to make, to draw conclusions more confidently. This person here, it's Eliezer Wright. He's the creator of the health insurance, the life insurance. And he said, while nothing is more uncertain than a single life, nothing is more certain than the average duration of 1,000 lives. So we really know things statistically. Of course, there are always different behaviors for individuals, but statistically speaking, we know things. This is the whole point of Monte Carlo and the whole point of convergence. As our sample grows, we start to learn more and we can rely more on our results. Now we'll move on to the sampling methods. So there are cases in which, you know, the function is not well behaved and there are many errors, and yeah, so we have different methods. The most common one is the inversion sampling. The second, the easiest one actually, it's the inversion sampling, which is based on the mathematics, the formalism that I've shown you a couple of slides ago. We also have rejection sampling, which is what we just did for pi, throwing darts on a target and hoping they reach the target. We have this importance sampling. We have stratified sampling. Yeah, just going to briefly mention them. And there are codes for all of these on GitHub. I'm going to discuss this towards the end, okay? So, inversion sampling. This is the trivial one, okay? This is the simplest Monte Carlo sampling method, and you don't really need to know that this is a Monte Carlo method to think of it. So when I was doing my first undergraduate research project, I stumbled upon something like this. I had a distribution from which I wanted to sample, and I didn't know how. So what I did is, okay, I'll make this distribution. I'll find the cumulative distribution, like this. And then I'm going to draw a random number, u. And then this random number, I'll just see where it intercepts my curve. which is a continuous curve, a monotonous function in the case of the CDF. And then I'm going to project this onto the x-axis, and I'm going to see what's the value of x that I've just sampled. So random number, the computer gives me this, okay? I get this from the computer, u. Computer gives me u, and I get x for this value. So as you can see, this is very intuitive way of doing things. You don't really need to understand anything about Monte Carlo. The discrete distribution case, it follows likewise. And the advantages of this method is that it's ridiculously easy to implement and to understand, but very few distributions have these nice CDFs that can be inverted easily and efficiently. Sometimes, you know, you are not able to really capture the small variations in the probability distribution function, and so on. Yeah. So this method, there are other methods as well. Okay, this works, but depending on your problem, there might be other better ones. We also have this rejection sampling. So rejection sampling is essentially the idea that we had with pi. We have a function that we want to sample from, like here it's f of x. We just provide a bounding function, which was the square in the case of pi. Here it's just this rectangle. In this other function, it's these two rectangles here. And then we start throwing points and just counting fractions, okay? Yeah, this is a very easy to understand method. The operations are very simple, okay? But the disadvantage is that this method is not very straightforward depending on your proposal function. And it's easy to imagine that if your function changes a lot, you have to make a very complicated proposal function, and then it becomes hard to start sampling from this proposal function because you have a very bumpy target distribution, and your bounding function, it's complex, and you don't want that. So this method is convenient when you have like this. You have 1 bump, 2 bumps, or 3 bumps, but when things are changing a lot, it works, but it might also take a lot of time because you might be wasting a lot of points, right? Your computer has to generate a random number, and this random number is either accepted or rejected. And of course, you want to have a decent sample. So you want to accept a lot. And if most of the numbers that you are generating are being rejected, most of the samples you're generating are being rejected, then it takes a long time to actually get what you want. Okay. This is the rejection sampling. We also are going to do an example soon. We have the importance sampling as well. The importance sampling is slightly more complicated, and it's particularly useful in cases in which your function is not that well behaved. The whole idea behind the importance sampling is the following. Just look here. F of x dx is equals to f of x divided by w of x times w of x dx. So essentially, we just multiplied and divided by the same function, which is just trivial, you know. The advantages of this method is that it can be applied to just any kind of distribution that you want, including those with discontinuity. So if you have like 1 divided by 1 minus x, and you want to sample it close to 1, this is probably among the easy methods, the one you could use. But this method is not as straightforward as the rejection and inversion sampling methods. Okay, let's write using a weighting function w to account for the regions where f requires more sampling, okay? So again, we have this problem. So we are going to take the average value of this now. So the average of f of x divided by w of x. So we are taking the average value. We know how to do that. We've seen, like, we had a long review on statistics now. So the average value is just this, the weighted average. And yeah, and here it's because we don't know what's the integral, the normalization of w, right? If w is normalized to 1, this is 1, and it doesn't make a difference. Yeah, but in principle, we have this it's easy to follow that we get I. I'm calling this integral I. And here, it's just a normalization integral. Now I'm isolating I get this. We can now just recast this W into a probability distribution function, which is literally just to normalize it to ensure that it's 1. So W, P of X, which is the probability distribution function, it's the function W divided by the normalization of W, the integral. Okay, so yeah, therefore, the function that we use to sample from, that we take a sample from, that's the function P, the probability distribution function. We sample from P, and we can write this summation here. As I told you before, we go back and forth between, like, you know, because we're implementing most of these things in the computer, you're always using sums effectively, but it's easier to represent like integrals and so on. So if we just do the summation, that will be n P of X, remembering that P is defined as this thing, and times f of X divided by W of X, okay? And then we also have this value of n here. The weighted average of f of X, so what we started calculating before, it can, again, I'm just transcribing what I've written before, it's this. And now we want to calculate I, and we can calculate I from here. We can just, we know that f of X, the summation of f of X divided by W, times the integral, so just the normalization of W, ideally this could be 1, okay, divided by 1 over n, where n is the number of samples. So this is how we calculate I, okay? So important sampling, it's essentially, yeah, what's important sampling? It's this function. Oops. We want to sample from f, we just multiply and divide by another function, period. That's important sampling. It's very simple. We are going to see an example soon. I'm going to show you this together with the examples. Yeah, I think now it's a good time for that. Stop sharing. Now I'll share the Monte Carlo. Yeah, this one. Okay, as I told you before, we've seen many examples starting with the estimate of pi. So yeah, to estimate pi, it was that this error here, I don't know what happened. I should probably fix it. Sorry. But the idea is the following. We had, like, we wanted to estimate pi. We had a circle inscribed in a square. And let's say that the circle has radius 1, which is the same size as the square. We just generate random numbers uniformly between 0 and the radius, which is 1. We want 100,000, so that's the number of samples you're taking. And then we just loop over these samples. We check for each event, okay? Each event we have an x and we have a y. We calculate x squared plus y squared. We see if it's less than 1, which is the radius of the circle. If yes, then that means it's inside the circle. The point fell inside the circle. Otherwise, it's rejected. So that's how we can calculate pi this way. And if we just plot it, you see that yeah, this is the actual value. You see that most values, the peak is really close to the actual value that we have. And the convergence, it takes place in like about 20,000 iterations or so for a sample of 20,000. Now let's start with the inversion sampling, which is the easiest sampling of all. So essentially the idea is we have f of x is equals to I. We just want to invert this. If you recall from what we've just seen, the idea of the inversion sampling is we are provided with a function x and y. But these functions, they are continuous in theory. They don't need to be, okay? They can be also continuous. But yeah, a continuous function is essentially a function. Yeah, when you pass this function here computationally, you probably want to pass like arrays, like vectors, with many points and with very tiny spacings, because that's almost exactly like the continuous function. So x and y here, they are vectors. And we want to take n samples, okay? So in the inversion sampling, we pass the probability distribution function, which here is y, and we compute the CDF from the PDF. We just ensure that it's normalized by doing this. And then, in this particular case, we select a random number between 0 and 1. And then we are going to look at the x-intercept of the random number we just generated. That gives us the x sample. And then we return it. If you apply this to a Gaussian function, the Gaussian function is shown here in black, the blue is what we actually get as the sample, which is pretty good, I would say. You can see that the shape, the behavior is more or less the same. Of course, you can improve this by taking an even larger sample. But this is already a start. This is how the principle of Monte Carlo. You get random numbers, you have a probability distribution, and you just randomly get things to reproduce your probability distribution function. For the acceptance rejection, yeah, we just have this function again. I'm going to take the easy case. So whatever the function is in this implementation, I'm just taking a big box around containing the whole function, okay? So here I'm taking the limits of the function, the smallest and the largest x's that we have on the function, the same for the y. It's just a big box around whatever function we have. If the function is very picked in one place, well, this is going to take a long time for the rejection sampling, but right now I'm just worried about showing the methods to you, just illustrating the method instead of getting an efficiency. And then I'm going to create empty lists to accept, so the samples, and reject values. And I'm going to draw randomly values within this rectangle, like in x and y. And yeah, if this falls under the curve, so if the random values that I just randomly selected now, I test if it is smaller than my probability distribution function. If yes, I accept it, otherwise I reject it, which is this else condition. And applying this to also a Gaussian, we have that the Gaussian is this black one. The gray dots outside, they are the rejected events, and the green ones, they are inside, they are the accepted events, and the blue is the sampled events that you got. So it's your sample, your actual sample, right? Again, it's good. It's close enough to the function that we wanted with some differences. You can always decrease the differences by increasing the number of samples that you are drawing. Okay? So this is the second example. The importance sampling, it's slightly more complicated, but if you remember, it relies on this multiply and divide by the same function. And then this function W, okay? So in order to implement it, okay, I'm just calculating first the function we need the function f, we need the function w. We are taking n samples. Now we are not taking a Gaussian to illustrate this example. What we are taking is this function here, which has something on one, like a singularity, right? At one, it diverges. And we are going to sample here this function using this routine. And this routine is essentially, we take an x sample, any value, and then we interpolate this in x for the function f. But it's important, yeah, I think my notation here might not have been the best one. But yeah, originally we had f. I should have called it something else. I'm sorry about that, okay? Yeah, but I think you can abstract. I'm calling now f, I should call this f prime. Yeah, I'm calling f prime this term, So just the exponential and W this term. And if I want to sample from this function, I can just sample from the function I'm used to, which is this one, the top one. And the bottom one, the 1 minus x, well, it does enter the calculation through the denominator, okay? So I'm just multiplying the total normalization, which could be 1, let's just forget about it. So I'm interpolating the top function and the bottom function. And by doing that, yeah, this is how I'm calling it. And here I'm enforcing normalization. So this is what we have. So the PDF that we had in the beginning, it's the black curve. F, it's the one, the numerator. So it's just the exponential of minus x squared. The bottom one, it's just 1 minus x. This is the sample data. As you can see, it agrees pretty well. Let's go back to the talk. Yeah, here is an example of the different methods as n increases, so as the number of sample increases. I don't know what happened with the rejection. Yeah, you can probably check this code on GitHub later. But as you can see, the important sampling converges much faster than this one. So let me go back. Yeah, you see, this one already kind of converged, and this one is still getting there. Because this function is not trivial, it requires more larger samples. And what about Monte Carlo integration methods? So as I told you, one of the main applications of Monte Carlo methods is for integration, in particularly for when you are working in higher dimensions, right? When it's multivariate. Before we move on to that case, maybe we can take a look at what we learned in the course of numerical calculus before, which is just the standard techniques for integrating, just for doing whatever integral numerically in the computer. Usually we have, the problem is this, we want to integrate f of x, and we usually just, you know, if we divide the space in same-sized intervals, very tiny ones, we can just, the easy way to calculate the integral is this, the easier way. Of course, there are other methods, like there is the trapezoidal method, we have like some Simpson integration and so on. That's more complicated. Let's just work with the simple one, just for the sake of comparison as well. Okay, so usually when we have functions that are not that easy to be, that are not that well behaved, we might, we can also do things like we did for the importance sampling. We can do this, right? And then we can calculate this integral here, which is much easier. But in the standard numerical integral, the problem is this. So yeah, we want this delta x, it's very small, but not infinitesimally small. Therefore, this is just a tiny step that allows us to approximate everything to a summation, okay? So if we do a Taylor expansion of this, it's essentially f of x0 times delta x plus the term with the first derivative, delta x squared, the second derivative, delta x cubed, and we can just rearrange all this as this equation here. So yeah, in the conventional integration that we have, the error at each step, it's of the order of the second derivative. At first, but the cumulative error, it's actually of the order of this delta x squared, because we just take the first term and then this other term here, it becomes the error, right? Our approximation is truncated here, this then is the error. So what we can say is that the error is of the order of delta x squared, which is of the order of n to the minus 2, where n is the number of steps that we have there, or the number of samples in the case of Monte Carlo. Okay, this O, it's not just an O for order. This, I don't know if you're familiar with this O notation. This is called Barman-Landau notation. It's very used in the in complexity theory and computational science and computer science. Okay, so this essentially tells us runtime and space requirements. That runtime and space requirements grows, how the runtime and space requirement grows as the input size grows. So the input size is just the number of samples in the Monte Carlo, or the number of divisions in the standard numerical integration with the usual methods. Okay. Yeah. So in 2 dimensions, we have that the cumulative error, it's also of the same order, right? Because in 2 dimensions, we multiply, yeah, I think I'm missing a square here. This will be then the error, but because we are in 2 dimensions, then we will take the square root. Therefore, yeah, we will fall back to the original case. What we can say is that in the traditional integration, we are always with this complexity of the algorithm. It's always n to the minus 2 for this simple method, not always, but for this method, sorry. Okay, and this complexity of the algorithm, I mean, yeah, we want the error to decrease as n increases, right? Therefore, this is good. Yeah, it's good for performance reasons. Let's see how our Monte Carlo method compares with that. So for the Monte Carlo, we have an integral, same thing, same way of opening the calculation. And we also can calculate the variance. That's why we spent that so much time in statistics before. So the calculation of the variance is like this. It's easy. So the variance of the integral, it's delta x squared standard deviation squared divided by n. And if we take the square root of the variance, which is order of the error, that's delta x sigma, so the standard deviation divided by square root of n. Therefore, what we can say, and yeah, so this the error of the integral goes with the square root of n for this algorithm. And if we generalize this result for the multidimensional case, it's essentially just one integral over different variables. The error is essentially just the product of delta xi, where I just runs over the dimensions. Therefore, what we can say is that Monte Carlo integrations, they have a performance of O, so of like complexity, n to the minus 1/2. This is great for performance. So if this grew very fast, that's bad for performance. But if n, as the number of sample decreases, our error also decreases. And yeah, so this implies that Monte Carlo integration methods provide us satisfactory performance, especially if we are doing multidimensional integration. So one example that we could do is essentially just do the pi example, the calculation of pi again. I'm not going to show you the script for that, but we can just work out the mathematics in higher dimensions. We can do the same thing, but instead of using a circle, we can just now use a sphere. And instead of using a square, we can use a cube. And it's the same thing. We have an equation of circle, x squared plus y squared plus z squared is equals to 1 if the circle has a radius 1. Then we can just isolate z. Then that means that z is equals to the square root of 1 minus x squared minus y squared. And we know that this gives us the volume of the one part of the sphere. And we can just count the number of hits like we did before. And this is kind of the results that we get. Convergence around 10 to the 5 samples. And as you can see, the peak is also very pronounced in the right position. So yeah, that's another application. And now there are also a couple of physical applications that I would like to discuss with you. I think in previous lectures, someone, probably Betty, showed you explained a little bit about radiative transfer, so how it works, what is it for, some important concepts involved. But I think it's worth recapping things like the concept of mean-free path. So mean-free path is something that comes up in a lot of astrophysical problems and also particle physics problems. And the idea is we have to decide whether or not an interaction occurs. And to decide whether or not this interaction occurs, let's take a look at, just to understand what's going on, at this drawing here. We have a slab. This slab has a total size L squared by L by L. And we throw something at it. I ask you, what's the probability that this, whatever, this particle I've thrown at this slab will hit one of these red circles? So these red circles, essentially combined, they give you something that we call cross section, which is measured in units of distance squared. So the cross section, it tells us essentially what's the probability of an interaction to occur. The mean-free path tells us what's the typical distance that a particle can travel before 1 over E of these particles interacted with the scattering centers shown in red. Okay? So yeah, you can, this calculation is straightforward. I'm not going to elaborate on it. You can, I'm pretty sure you've seen this before anyway. So if you have a beam of particles traveling through a medium, so how many of these particles will interact in the first step? That's basically given by this. We want now to understand this in terms of Monte Carlo. So what Monte Carlo can tell us about this? Well, using Monte Carlo methods, all you have to provide is the mean-free path, and then we'll get an actual distribution for several particles according to this law, right? Of course, there are some particles that will travel 2 mean-free paths. Some of them will travel just half. But in the end, we'll get this exponential behavior as expected. Physically speaking, computationally speaking, a very similar problem is the problem of a particle decay. It travels a little bit and then it decays. But instead of the mean-free path, we have a typical decay time. So that's what I leave to you as an exercise, which is essentially to do a calculation for extragalactic neutrons. So neutrons are not stable particles. Neutrons have a lifetime of the order of 880 seconds on its own rest frame, okay? But if we go to very, very high energies, neutrons, of course, there is a Lorentz boost, right? The mass of a neutron is, roughly speaking, it's I think 940. It's of the order 940 mega electron volts divided by the speed of light squared. Okay, so that's essentially 1 giga electron volt. That's 10 to the 9. So if we have a neutron with energy 10 to the 12, that's already a Lorentz factor of 1,000. That means that due to relativistic effects, the neutron will be able to travel 1,000 times more than this proper time. Okay, this is just Lorentz transformation. This is not the objective, but it's an interesting example. So what I'm proposing here to you is to consider this problem. We have a gamma ray burst with a given luminosity 10 to the 46 ergs per second, out of which 0.1% of this energy goes into the neutron beam. But neutrons decay, as I told you. So the question is, how far can these neutrons go? Of course, they can go, just intuitively think that they can travel 882 seconds, and you convert that with the speed of light, to convert that into a distance. That's how far this neutron can travel. But the exercise is to write a Monte Carlo code for this. You know that the neutron lifetime is essentially an exponential decay, e to the minus t over tau, where tau is the lifetime. You have the relativistic, the Lorentz factors here. So just perform the exercise to perform a Monte Carlo simulation for this, plot the flux of neutrons observed at Earth as a function of the distance of this object, this gamma ray burst. And this distance should be 1 kiloparsec, 10 kiloparsec, 100 kiloparsec, or 1 megaparsec. This actually, it's something interesting, and it will give you some physical insights, which I'm not going to give you spoilers, but yeah, after you do it, you're going to see that something physically interesting comes out. Okay, and my last slide for today is this. Quite often, well, I don't know how often it is, but if you're working in with radiative transfer, for example, or particle like light scattering, you have light, it bumps onto something, and then it scatters in another direction. Quite often, this scattering direction, it's isotropic. It can go just in any direction. How do you sample any direction? So, for example, if I want to look into the sky and see, on average, the same number of particles in all directions, so isotropically distributed, how do I actually use Monte Carlo method, what we learned today, to sample things in the sky? I personally found this problem. I learned this the hard way. So during my first undergraduate research project, I had some arrival directions of things in the sky, and I wanted to compare with the isotropic case. So the isotropic case is like same amount of things in different directions of the sky on average. Then I said, oh, this is trivial. I just have to sample from a uniform distribution in azimuthal angle and then in zenith angle. I did that, and what I got was this left plot. So there was a concentration close to the poles. It took me some time. Yeah, I have to tell you that some time for me was like maybe a whole day. I had this problem like in the morning, and in the evening, I kind of found the solution. I kind of got the solution on my own, because yeah, I was on my undergraduate research project. I never learned this, and I'm slow anyway. So it took me some time to actually figure out why. But then I said, okay, let me just write down the probability distribution function as a function of the solid angle. So omega here is a solid angle. Oops, I'm pointing in the wrong screen. It's the solid angle, okay. So you know that this is the probability of phi times the probability of theta. You can just separate the integrals, but you see that there is this sine theta term here. That's why we get this excess close to the poles. The proper way to do it is to sample from this distribution, okay? So you just get a chi, I think it's chi, xi. Okay, I assume that I forgot. I think it's key, it's slash chi in LaTeX, yeah, whatever. So you just get this symbol here in the interval 0, 1. So this is just a random number that you generate, and you multiply it by 2 pi, then you get the azimuthal dependence, which is uniform. But for the theta dependence, you have to do this. You have to calculate this integral, and then to sample the theta angle, you get cosine, inverse cosine, arc cosine of 2 times this random number minus 1. I have the example here to show us. I'll stop sharing the screen. Okay, now let me share the example. So I think you can see it. Sharing this screen now. This is again the GitHub. Let's take a look at this. I call this particular example sphere point peaking. It's just a very trivial implementation of what we've seen there. Why is it not displaying correctly? I really don't know what's going on, why it's not being displayed correctly. I should check. Yeah. So anyways, phi, we just draw a random number between 0 and 1. and then we multiply by 2 pi. But theta, we have to use that arc cosine expression from before. And drawing n samples between 0 and 1 uniformly. And if we plot it, the distribution of azimuthal angle is this, but the distribution of zenith angle, it's not the same, it's not uniform, it's curved. That's why when we do it wrong, we get a lot of events in the pole. If I plot the sampled events, you can see it's isotropic, great. But if I do it in the wrong way, as I've shown here, you get an excess towards the poles. That's the wrong way to do it. Therefore, just to finalize, now that we've seen this example, yeah, Monte Carlo methods can be used for several applications. So far, we've seen the sampling methods, inversion, rejection, importance. It can also be used for integration, and it, you know, anytime you have to draw random numbers from a sample, that's a form of Monte Carlo. That's what we do, like a lot professionally. For data analysis, we do that. For simulations, we do that a lot. And in many other applications, as we'll see later. For the next lecture, we are going to come back to this. We are going to start talking about random walks, and then introduce Markov chain Monte Carlo and everything that comes with that. Okay? So I'll see you next time. Bye.